So I'm Phaedon Kyriakidis. We will be doing the theory part of the Geostatistics module for the Medsal Summer School. The idea is not to faint or to get lost in the equations, for those of you who cannot read the equations, and provide a more intuitive idea about geostatistics and what is it all about and what is its usefulness in the business of hydrogeology and salinization in particular. So it's essentially a branch of statistics that's been around since the 60s, based on the mining legacy of South Africa, and especially Professor Matheron that essentially coined the word kriging. Kriging is essentially a regression approach to estimate unknown values at non-sampled locations from known data, which is essentially the idea behind spatial interpolation. And key applications of geostatistics involve the characterization of attribute variability in space and time. That means try to understand the texture or the correlation behind the data. That is one key ingredient to spatial interpolation. So with different forms of kriging, kriging is the word for the geostatistical workhorse of interpolation, we can integrate different data to estimate or predict the unknown values over a study area, be it in 2D or 3D. We're going to talk essentially about spatial correlation and spatial interpolation, and a little bit about what are different extensions of kriging that allow us to use different variables, like in a regression setting. The geostatistics has been used a lot for sampling designs, but we're not going to cover this at all. And we're going to we're going to spend some time on seeing how we can use simulations in a geostatistical context to propagate uncertainty of parameters like hydraulic conductivity into model out. Okay, so some books on geostatistics for those of you that want to get involved in this further on. It's a widespread application set. Within the Medsal context, there are two modes of application of geostatistics. One is the standalone mode, essentially without physical models involved, which means that we might be using geostatistics to characterize variability and perform modeling, statistical modeling on data on geochemistry, for example, like groundwater salinity indicators, different ions and cations, or geochemical elements. Essentially, classical approaches here is to create maps of the variables, either individually, that means, let's say, concentrate on cadmium, concentrate then on magnesium or other elements, or jointly. This is this part here. Jointly means that trying to understand how all these variables also are linked together. This is the context of, let's say, principal component analysis or factor analysis, combined with geostatistics. And the idea would be here to predict the distribution of these elements in space and time, right, with the uncertainty. The other working context in Medsal is in conjunction with physical models of essentially flow and transport of flow, basically, and then transport essentially and reaction in terms of geochemical and geochemistry and thermodynamics in the aquifer. And there, where in that part, geostatistics is used to essentially model the spatial variability in conductivity and create spatial maps of conductivity, which are then used as inputs to these models. More generally, geostatistics is being used a lot in what is called the inverse problem in hydrogeology, where an inverse problem essentially is a classical one, is to estimate hydraulic conductivity from conductivity measurements and piezometric head measurements, and maybe other types of tracer tests. These are just some examples of how essentially the oil industry also is linked to the hydrogeology industry, and the methods are common. A lot of research is going on integrating data from geophysical surveys into reservoir characterization or aquifer characterization. Right, so we're going to be flying a little bit lower than this. In a sense, we're going to give an overview, an introductory overview, and then we're going to do in the second part where the practical applications are. We're going to use the software R to illustrate some of these concepts, and of course open the floor for future interactions if need be. So the setting would be typically either you are in a data poor scenario where you're here. Data poor means depending on how many boreholes you have, you might be filling in this space with a lot of data. And you might be also having some kind of indirect information, be it geology, be it some kind of a geophysical survey that might be linked to the attributes that you're trying to map. So these are examples of different attributes that might be of interest in this context. And you can also play scenarios with what would be this image, which is essentially typically more abundant data, but indirectly sampling, linked to the objective of the mapping. So the idea would be to fill in this space with values. That is the idea of spatial interpolation. When we use the word spatial interpolation, we typically assume that we don't have any other data of other attributes. And the word spatial prediction is also used for implying that you have also different variables involved in a regression context. So spatial prediction essentially is an expansion idea. You want to expand your data beyond the points where you have them. To make this expansion, you need to have some kind of models that will allow you to assess how far a particular value can go beyond the sampling location. That is where the concept of spatial autocorrelation comes into play. So imagine that you're, let's say, sampling elevation in Sahara, all right? And if you have a measurement of elevation in Sahara, that measurement might take you a long ways around it, because essentially the relief terrain elevation in Sahara is very smooth. So that license, that influence of a single point around it is essentially a function of the smoothness of the attribute that you're looking into. So if you're interpolating, let's say, elevation in the Alps, then the variability of elevation is much more higher and faster essentially than Sahara. So your data are not able to be expanded too far out from their places, right? So the basic notion is that geostatistics essentially looks into the spatial variability and the spatial smoothness of the attribute and tries to model that before it makes interpolations essentially or simulations. So the classical tool for modeling this kind of smoothness in space of an attribute is the variogram, right? And the variogram essentially is a measure of attribute dissimilarity variability. So it's essentially we measure how dissimilar, this is a measure of the similarity between attribute pairs. We're going to see that in a moment. So the variogram essentially increases with the function of distance. So this is distance here. So that means that the further apart you measure two values of an attribute, on average, you expect that these values will be more dissimilar the further they are apart. Right? How dissimilar and with how fast this dissimilarity essentially rises, that is what the function of the variogram gives you. So here we have a variogram along the horizontal direction. and along the vertical direction. And along the vertical direction, you see much more variability. That means that there is more dissimilarity. So in this plot here, this part here is the vertical variogram, because essentially it is rising faster up to the point of the seal, which we're going to see in a moment. And this variogram here is the horizontal variogram, because it rises slower than this one here. So the range here, the range of the variogram, is an idea about what is the correlation length, essentially, of the process, of the attribute. This is about 10, which is on the vertical side, and this is about 40 here, which is on the horizontal side. Right, and you can see how things can become more complicated if you have faulted domains where you have to essentially follow the variability, and that means that you, in order to deal with faulted and and bounded essentially and rugged essentially sedimentations that are faulted or curved, essentially you need to build a new system that unravels that and makes it mostly like this. So once you have these in place, the idea of a variogram or a correlation function, which is very similar to the variogram, you can then try to see whether you can actually make predictions. So here is an optimal, as we call it, minimum variance prediction of these data points here, data values here. And if you have other variables that are linked to the observations, you need essentially to see how these are related, either with regression models or with extensions of the variograms to account for two different attributes. So in the case before, the pairs here, the dissimilarity is between attributes, between data of the same attribute. That's called an autovariogram. But we can also have the similarity between pairs of data pertaining to different attributes. This is called the cross semivariogram. So using either regression models or cross semivarograms and other types of regression models, we can also integrate these other types of data into the prediction and essentially make a map that is more realistic, let's say in this case, than this smooth version here. Okay. So the word statistics means that there is variability and uncertainty involved and probabilities somewhere in the process of statistics. And that means that the output of kriging essentially is not just a single value. Right? So kriging gives you two outputs. One is the prediction itself, which is here, right? Using, let's say, the hard data, the few direct measurements. And here is using both the few direct measurements and the other indirect measurements that we saw before. So these two versions are associated also with the corresponding uncertainty. So this is just a zoom out map of this. Now here we're depicting the uncertainty in the prediction, right? And there is a minimum and a maximum, which we don't care really for now. What we care is that the moment you include the other types of data, that uncertainty map becomes, the magnitude of that uncertainty becomes smaller. So you can see here, this is a common scale to both of those, the color scale. You can see where the data are. The data are where the uncertainty is smaller. Actually, it can come to 0. And the further you are going away from the data, the more uncertain your predictions are, depending, of course, on the variogram model and the complexity of the configuration of the data, as we're going to see in a moment. All right, so there are two outputs from kriging. There is a kriging estimate and the kriging variance. These two outputs define actually probabilities. So if you were to drill, let's say here at this point number 1 and at this point number 2, kriging would give you the estimate and the variance. These two actually are the mean and the variance of a distribution here that we can imagine. And depending on the flavor of kriging, whether it is vanilla or Gaussian kriging or whether it is non-Gaussian, log normal, or other types of kriging, this distribution has different shapes. Most of the times, and the easiest way to assume stuff is to assume that this is a Gaussian distribution that has the mean equal to the kriging estimate and the variance equal to the kriging variance, this corresponding variance here. All right, so if you're close to a high valued data point, that mean is going to be high and that variance is going to be low. And if you're away from the data, let's say somewhere in the middle, that mean of the distribution, there is another distribution here, which I don't show. That mean will be close to this blue value here, and the variance of that distribution here will be higher than those because these 2 points of inquiry are close to data. Right? So if I was to make a distribution here, in this point here, this would have a larger uncertainty, larger variance. And here are the corresponding distributions once we include the other data source. And here we performed actually co-kriging, which is a way to introduce into the mapping exercise the extra information from the auxiliary data. So here is the kriging estimate, and here is the co-kriging variance. These are smaller variances, so the distribution is actually more has a shorter variability than the previous case. Okay, so no matter first of all, we all understand that with few data points, even if I sell you kriging or splines or whatever method, super duper method I can dream of, few data means smooth maps, means essentially classical bullseyes. Bullseyes are, if you do ISO lines, you can see stuff around the data locations. There is no way you can actually create, you know, the best map. If, for example, if there is if there is a let's say a high valued area and you have not sampled it, only with few data you cannot recreate it. All right, so the idea of a high valued area, let's say for hydraulic conductivity, would be essentially missed, and we need to either introduce more data or indirect data that might be linked to the hydraulic conductivity so we can map it better, or try to understand how this missing variability that we're not capturing impacts our work. All right, so the caveat of any prediction algorithm is essentially that the map might be optimal, but it might not be optimal in a sense that reproduces the correct spatial variability. And a lot of the times, actually, that uncertainty is rather forgotten than used. Unless you're doing simulation, which we're gonna talk about in a moment, basically most of the applications of kriging are that I've seen in a lot of applications that I've seen in hydrogeology essentially would like to use kriging just because people hear it's a method that people use a lot and it's a good method. But at the end of the day, if you're not using the uncertainty, you might as well use another method to begin with. All right, so the idea behind simulation is simulation actually has a different objective. Simulation is seeking to generate simulated values of the attribute, let's say conductivity here, in such a way that the simulated map has the correct spatial variability, and that correct spatial variability actually comes through the variogram model. So kriging, even if it uses the variogram model, at the end of the day tries to give you the best estimate at a single point. All right, so that best estimate at a single point, when coupled with another best estimate at another single point and another single point, creates a kriging map. That kriging map does not have the same patterns of variability as the variogram imposes, because it was not meant to do this. Simulation, on the other hand, goes at creating images that look like the variogram should like the images that would come through this variogram model, and I'll show you in the second part of the lecture. So here are two realizations conditional to the data. Conditional means that they reproduce the data where we've measured them. That means that nearby high valued areas, there will be high numbers. Nearby low valued areas, there will be low numbers. But from one realization to another, there's going to be differences, right? And those differences going to be more where you have few data control, where there's few data, and will be less different where you have a lot of data. So here, the simulations will be more similar. Here is two realizations using both this data and the indirect data we talked about before. You can see that these realizations now are more similar to one another because they share this information that is common to both, and of course the few data points. So the simulation aims at creating maps that have a model of spatial variability dictated by the variogram. They are not, so each one of those is not the best map you can get, but all together they serve a purpose, which I'm going to illustrate in a moment. And the goal here is to create those images so that they produce the data at their locations, as actually kriging does, and other methods, of course, do. And they also reproduce the variogram model and the histogram of the data. Right. So the most widely used algorithm for generating simulations that are covering a lot of nodes, so large grid nodes, are actually sequential methods. And those methods call for essentially transformation first of data to the Gaussian world, either through logarithmic transformation or through other kinds of normal score transforms. And then what you do is actually you create a visiting sequence. So here is an example where you're simulating point pixels at a fine resolution using in principle you can use both coarse data, the yellow ones, and fine resolution data. So what we do here is we're visiting small pixels at random, and the first time we actually come to a node, there is nothing here, so we draw from a global distribution. Then this value is simulated here, and then we go forward to another place, and then we look around us, we see how many original data we had, how many previously simulated data we had, and with these data we do kriging. We estimate the local mean and the local variance, the estimate and the kriging variance. From that Gaussian distribution, we generate a number. We call that a point, a simulated attribute value. We put it as if it were a new data value. So here is at the point where we're sitting at. Here around us might be data that are from these red pixels. Some of those might be original data values. Some of those red ones might actually be previously simulated values. So we visit things at random, each time doing kriging with the original data and the previously simulated data until we visit all the small, let's say, pixels here on a grid node. And in principle, you can use data that are of the same attribute, of different attributes, of the same area, small points or big blocks, and you can fill in these space of small values here. Once you're done, you back transform all the results to the original space, and that becomes one simulation. So these simulations are typically coupled with physical-based models in a Monte Carlo framework that is called uncertainty propagation. So we have a model. The model is a flow transport model that has some fixed inputs, and some variable inputs are called parameters. One of the most famous parameters of this flow and transport model is hydraulic conductivity. Right, so we know that hydraulic conductivity is measured at few points. That any map is actually has a lot of uncertainty, so that is called parameter uncertainty. So we would like to propagate parameter uncertainty in the hydraulic conductivity through the repeated evaluations of the model to essentially a model output. Here is a concentration of solid. A solid is released from a central well, and we essentially monitor when it will reach one of the four corner wells, which are observation wells. Right, so this is a flow and transport problem, and one hydraulic conductivity realization is actually fed as an input, let's say to FEFLOW or other models. These create one output, and then we can see after how many times, how many steps we concentration reached a well. That is called first arrival time, and you can do this another time with another hydraulic conductivity simulation, run again one more the model once more, see this first arrival time and build a distribution of first arrival times. Right, so this distribution you would like to use, first of all, you would like to be representative. That means that you need to, most of the time, run a lot of simulations here of hydraulic conductivity in a geostatistical way, feed them through the model to create this output so you get this histogram. Right, so this histogram then will be used to make decisions on whether to whether this is a probable zone for remediation or so and so forth. Right, so this is your decision variable in all of cases. Right, so I'm going to motivate this example even more with an even more simpler toy example, which actually in my mind is quite an eye-opener for why we need to worry about uncertainties and use essentially the geostatistical flow chart workflow to get it at the end as we speak. So here is a simple toy example. We have two cities A and B. They are an engineering firm wants to install an underwater cable. All right, and in order to install that cable, it needs to understand the cable length. All right, so let's pretend for now that this distance here is 200 units, whatever units they are, and that there is a true seafloor, which we depict here. This is again a simulated seafloor, but we can pretend it's the truth. All right, and let's pretend that for two consecutive points, the cable actually can be straight. So we ignore the effects of let's say we don't have a curved cable hanging from two places, but we have essentially a straight cable. Essentially, in order to find the length of that, if you know the length of the cable, if you know the depth of this and the depth of the B point, you need to essentially use Pythagoras, sending the hypotenuse of a triangle to find essentially the difference in height or in depth between two consecutive points, their distance, which is fixed, which is 1 unit here, D. And if you employ this, essentially you get that this true cable length would be 662 plus the depth of A and B, whatever that is. All right, so the unknown C depth is this, which is then use the unknown values, the reference values, we pretend we know them. All right, then the reference is 662. From this, we actually sampled 15 data points at very good places that actually highlight a lot of the major features of the seafloor. So these are not bad data points. And we would like then to recreate that seafloor depth For doing so, we used kriging. You can use any kind of other interpolation algorithm. And when we use kriging, we use the same Varga model that we used to simulate the floor, the seafloor depth. So we essentially we cheat once more, and we take the reference Varga model that was used to create the correct seafloor. So there's no uncertainty in the Varga model here. The interpolated depth is here. You can see it reproduces the actual data values. So it means it passes through the data points. And it does so in a smooth version. That's called a generalization, essentially, of the true seafloor. And if you were to take these interpolated seafloor depth and employ the same formula as before, z hat now is the kriging derived values, you get an estimated cable length, which is 367, which is almost 50% an underestimate. And that underestimate is because simply you're missing the jiggles and wiggles. That means the short scale variability of this particular problem. And this is critical in this particular case. All right, so simulation aims at creating maps of, here, seafloors in this case, that are of similar ruggedness as the Vargam implies. So a Vargam model implies in it a model of a map of an attribute, and that map of an attribute exhibits some smoothness. We're going to talk about that in the second part of the lecture. So that smoothness is that roughness is what the simulation aims at reproducing. So here is one simulation, the one with a more intense bold line, and you can see that it passes the data points, and it actually also looks like the true floor in terms of the ruggedness. If you were to compute so this is one simulation, Z1 is one simulation. If you compute the cable length, you can see that here is 631, which is a 5% only relative error. The bad news is that there is no one simulation, so you need to generate many of those. And all of those would actually be reproducing the data values where you know them, the histogram of the data, and the Vargam model. And these essentially are called an ensemble of realizations. And essentially, it's a model of uncertainty about the unknown seafloor depth. And the larger L is the number of realizations, the better that model becomes. Right? So you can not only use 3 or 5. The idea is you can simulate hundreds of those. Right? So, and part of the research we're doing in the MEDCEL framework is to be able to generate simulations that are representative of more simulations, so that you cut down the cost of running these through a Monte Carlo procedure. So what do you do with those simulated seafloors? Well, you compute the cable lengths, and then you construct the simulated cable length distribution. So here is the distribution of simulated cable lengths. The estimated cable length through kriging was somewhere here, 367. And here is the true cable length is 662, which is close to the average of the simulations here, right? So the idea here is that your decision of the company is based on the cable length, is not based on the depth. The problem is that the cable length needs depth to be estimated, but at the end is this distribution that is needed. Why is this distribution that is needed? Because having this, you can actually you can make all kinds of analysis, and you can actually decide which would be the best estimate of your cable. And that essentially is the realm of decision making under uncertainty. In order to do so, you need also to quantify the costs and benefits, of course, and you need to also to quantify what is the impact of an error. So if you were to say that the cable length is 700 units, but it was actually 600 units. That difference, what is that cost you? Right, so this is called a loss function, and actually converts prediction error to dollars or euros. All right, that's the idea, and essentially that leads you to identifying what would be your best estimate to work with. For example, if your underestimation and overestimation are symmetric, not as is there here, if one increment of underestimation is costing you the same as one increment of overestimation across the board, that means that you would be using as your best guess somewhere in the middle, the mean or the median. Right? If your risk, essentially, if your overestimation would cost you much more than underestimation, then essentially you would be holding down to essentially the correct way, the correct quantile. So depending on whether you are risk neutral, risk prone, or whatever, you will be choosing aspects of this distribution. The idea is, what I'm trying to say is that if you want to make a decision, the mean of a distribution is the right decision if your loss function is symmetric. All right. In any other case, which is a lot of cases in reality, your optimal value would be a quantile to the right or to the left of that mean value. So a low value or a high value. So so that's the utility of having simulations and having a distribution of a decision variable. So in many cases, the hydraulic conductivity is not a decision variable. We need to pass this hydraulic conductivity through a model. So the decision variable will be, let's say, the first arrival time distribution. So what I'm trying to get at is that we need to propagate uncertainties into the inputs through whatever models we use, and these models need not be physical models only. They could be also models of, let's say, defining, for example, hydrochemical phases or categories, and what would that entail in your analysis. We need to use simulations to make this uncertainty propagation work. Here is just a closing statements here that the mean, this is the mean of all values that we simulate at a point. They would be very similar to the Kriging estimate, all right? And the variance, essentially the variance that we simulate, the variance of simulated values at a point would be very similar to a Kriging variance as the simulation increases if the data were Gaussian. So here is an example of your uncertainty as you go away. This is plus or minus 2 standard deviations. As you go away from the points, you can see these classical sausages. At the data locations, uncertainty is small, and as you go away from the data locations, it's high, right? And now, if you were doing Kriging, you would have these uncertainties, but the question is, how do you combine those uncertainties to come up from a set of local uncertainties about depth to uncertainty about the cable length? That is a difficult problem, not always doable. From simulation, you can always do it. Right, so closing this, we will see, especially in the second part of this tutorial, we'll see the ingredients of varograms and Kriging. We will not see other stuff around simulation apart from the tutorial of the practical examples. All right, so we're gonna go into more detail on varograms and Kriging, which are the workhorse of simulations also, and we're gonna not cover any other, other stuff about simulations and algorithms and whatnot. But the general idea is already given. Okay, so this is the first part. So we're gonna talk about the spatial varogram and the correlation functions, and how do we use those for characterizing attribute variability. I'm gonna define some notation. Z is the attribute here. C is the coordinate vector. I is the index, of course, N is the number of sample data. Um, and the first thing to do will be to try to quantify essentially dissimilarity or similarity. In general, Sij would be a measure of either similarity or dissimilarity. It's a function of two values that's called pairwise dissimilarity. And in order to not carry all this notation, Sij means something that relates the z measured at location I with the attribute, the z value measured at location j. And to cut corners short, the easiest way to do that to ask, oh, value at zi, are you different and how much from value at zj? Right, and that difference we can square it because we don't care whether one is higher or lower, or we can make it actually unitless by standardizing with something that has squared numbers, and that something is the variance of the attribute. All right, so if I want to ask the Borehole value at Zi, how different it is from Borehole value at Zj, if we're talking about conductivity, or the precipitation of I, different precipitation on J, and I want to get rid of those numbers which are squared, because they're unit squared, I can divide this by the variance. The absolute difference would be another one. And these three actually measure dissimilarity, and believe it or not, even if it's hidden in the context, if I compute this Zi minus the mean times Zj minus the mean, that cross product, as we say, is actually a measure of similarity. So this measure of similarity can be divided by the standard deviation to make it unitless and unitless here. So these are just metrics of pairwise similarity or dissimilarity for a single attribute. We might have situations where we have multiple attributes measured at the same n locations. So here is the data matrix that typically is actually having columns to be variables. So one attribute measured at all data points is one column, and the number of columns is the number of attributes that we measure. All right, so now we can talk about similarities or dissimilarities across the rows here, because one row pertains to a single point, has multiple attributes measured, and another row it's at another point for another sample point and has other multiple attributes measured. All right, so the idea is I want to compare now dissimilarity at two data points that are characterized by more than one variables. All right, and the idea here is that you compare row 1, let's say, with row I, or row I with row j. Okay, so Zi is actually the ith row of matrix big Z in a vector format, vertical. Zj is the other row in a vertical way, and essentially now we need to compare these two to say how different they are. And this comparison is a classical, for example, way. We could say, for example, if let's say this is chromium, and this is magnesium, and this is whatever, chlorium, then we can say the overall dissimilarity is chromium here minus chromium there squared, plus magnesium here minus magnesium there squared, plus chlorium here plus chlorium minus chlorium there squared. End of the story. So that is essentially the Euclidean dissimilarity between these two data vectors. If we don't like Euclidean and you would like to stick with Manhattan, which is the absolute numbers, you can say whatever, I don't remember, attribute 1 here minus attribute 1 there square, sorry, absolute value, plus attribute k here minus attribute k there, absolute value, and so forth. And if you want to get rid of the units, you divide by the standard deviation. This is the standardized square Euclidean dissimilarity. and so forth. So any way you cut it, you can estimate either univariate dissimilarity or multivariate dissimilarity between two locations, all right? And at the end of the day, you can arrange those dissimilarity values in a matrix. And let's say if we're talking about dissimilarity, essentially here we're computing the dissimilarity of Z1 and Z1, which is 0. And here with this dissimilarity between Zi and Zj, which is 0 again. So if this is a dissimilarity matrix, it will have zeros in the diagonal. The first row will contain the dissimilarity between location attribute, location 1, with all the other locations the same attribute. This here is the attribute at location I, the dissimilarity of that, with the same attribute measured at other locations. Right, so here is a corresponding color-coded dissimilarity matrix. If you have here 77 measurements, which are stations of precipitation, it's a 77 by 77 matrix with numbers here. The large numbers say that, for example, this particular value, the 40-something value, is different than the other ones, as is also the 20-something value, because it has high dissimilarities. A classical value of dissimilarity, which is embedded in the variogram, is Z here minus Z there, squared divided by 2. Divided by 2 is where the semi part of the semi-variogram comes in. In the same way, we can also measure the distance, the geographical distance between the stations, and we can create a n by n dissimilarity distance matrix, zeros on the diagonal, and then we can essentially pair those. So we can make a scatter plot of the distance between 2 points in space and the corresponding dissimilarity of the attribute values measured at those points. This is called a dissimilarity cloud. Right? The more you go up in distance, the more dissimilar are the Zi and the Zj at those locations. So when we are using the dissimilarity Zi minus Zj squared divided by 2, that's called the semi-variogram cloud. And if we're talking about, you can also have an absolute dissimilarity. And if we're talking about similarity, that's essentially a correlation or a covariance cloud. So this goes down with distance because it measures similarity. Now, because these are not too useful, we try to group data pairs according to the distances they are separated. So the user will actually define distances between, for example, here 0 and 0.25, 0.25 and 0.5, and we'll group with different colors. And let's look at the variogram cloud. So all these blue numbers correspond to pairs that are separated by distance up to 0.25. These green dots correspond to pairs whose distances are between 0.25 and 0.5 and so forth. So with this binning, you can come up essentially with different partitions, so these are called lag distances. So the user can specify more than one, and then depending on the lag specified, here are the pairs of data points linked. Right, so these are the pairs of station pairs within distance 0.25, and here all the pairs between distance 0.25 and 0.75. Once you do that for different distance classes, which are called again lags, you can actually make a distribution of those numbers, right? So instead of color coding them blue and so forth, and yellow and green, this is a distribution of those numbers within different bins. And the distribution has a mean and has a median. And we typically are interested in the mean, which are, these are the asterisks here with the bold. All right, so at the end of the day, what we're doing is we're taking dissimilarities, pairwise dissimilarities with distances, and grouping those dissimilarities according to distance classes to create an average dissimilarity. So this plot here says that there are 236 pairs within distance 0 to 0.25, those have an average distance of that much, I don't remember how much it is, and have an average similarity of 0.4. There were 654 pairs between 0.25 and 0.5, average distance that much, and average similarity 0.5. This is called a semivariogram plot, a sample semivariogram. Right, so this is essentially the formula that you can see in different books. This is an average of dissimilarity squared divided by 2. The 2 can come in. Right, that is the version of a semivariogram that you will see and you will compute. So the semivariogram rises with the function of distance. It has pairs, and we're interested in the average dissimilarity of attributes within distance classes. The semivariogram can be directional, so you can be very specific on the direction which you compute the variogram along, or can be omnidirectional, which means you don't care about the direction as long as they are within some distance limits. Here are directional semivariegrams of elevation along, this is along the blue here, is along this direction because it has the smaller variability than this direction, which is the larger variability. If you travel along this direction, you see more differences. And that variogram is actually this red variogram here. Okay? And here are the corresponding correlograms of this elevation map. Now, in order to compute those, the directional variograms, you need to specify an azimuth, which is different clockwise from north. You need to specify the lag distances, how many of those. You typically also specify an angular tolerance. So you don't only want data that are exactly, let's say, 6 degrees azimuth, data pairs, but you allow for some tolerance. Typically, this is always 22, half of the 45 degrees, essentially, tolerance. And at some point, you also need to specify a bandwidth so that your sector here does not become a big number, a very big sector. So these are trial and error specifications. There is no golden rule for that, and we need to actually make different tries here and then see whether there is a resulting pattern of variogram arising. The variogram needs to be modeled. Right? The sample variogram are the blue dots, asterisks, and the model is a curve which cannot be any curve you dream of. It has to be a curve that comes from specific models. One is the exponential, another one is the Gaussian, the spherical, and there are programs that will actually make the curve fitting exercise for you. The programs need to, most of the time, need you to supply them an initial guess for 3 parameters. One is the seal. The seal is where the variogram reaches a plateau, if it reaches 1. And the seal is close most of the time to the variance of the data or somewhere there. Now, the distance at which this curve levels off, the distance is called the range of the variogram. And that actually corresponds to the correlation length. So if I was to make a correlation function, a correlogram here, starting at 1, going at down, I would fit it with something that starts somewhere here with going at 0. Where this goes to 0 is essentially the correlation length. That means that pairs beyond that correlation length are on average not correlated, which means that some pairs might have a strong correlation, some pairs might be very dissimilar. On average, beyond, let's say, 1.5, whatever distance units these are, they will be uncorrelated on average. All right, so the range of the variogram actually gives you some pairs might be very dissimilar. On average, beyond, let's say, 1.5, whatever distance units these are, they will be uncorrelated on average. All right, so the range of the variogram actually gives you an intuition about how far or how close data are in terms of the attribute similarities. So for example, If I say I have a value, let's say that the range was 1 or 1.5. All right. If I give you a value at some point here, and I'm asking you how far out you would trust this number, or you would look at this number to give you information, the answer would be 1.5 units. Because beyond that, on average, I don't expect any links between data. All right. Here is a variogram that corresponds to a pure noise, random, essentially 0 always at the origin, immediately reaches the seal. Here, the variance of this data was 10. All right. Here is the variogram that is characteristic of a very smooth, typically like a pressure field. Pressure, temperature fields are having typically Gaussian variograms, parabolic at the origin and levels off. Right. This is a variogram of a spherical variogram, linear at the origin, or exponential, I don't remember. This is could be of geochemical concentration, porosity, and so forth. Is the addition of noise into the image that corresponds to what we call a nugget effect. Right? So this is the third parameter. The third parameter is discontinuity at the origin, and that corresponds to noise or random variability in the image. And you can see here the difference. So these are the same images with just addition of noise in the second case. Here is an example of a periodic, pseudo-periodic variability. This is an image of we call it, I don't remember, plants, right? So these are plants that have this spherical shape and are embedded into dirt, soil, right? So if you're looking at small distances, chances are that you are either within the soil or within the plant. So variability is low. Once you start looking at larger distances, and the similarities are larger distances, you might be mostly in the plant and in the soil, which means variability becomes large. At some point, beyond these distances, you start essentially jumping over the plants, and you're either within the soil, both ways, or from a plant to another plant, and then variability goes down. Okay, so this pseudo variation is shown in the variogram. Here is a variogram of a trend, which means that something is rising with no seal. There is a trend in the data. There is a systematic variation from west to east here. Here is a classical example of anisotropy. We have of a direction, on this direction, more continuous, which is this red variogram, than the perpendicular direction, which is more variable, and this is the black variogram. Here is an example of an extreme anisotropy that actually goes to zonal, what we call zonal. Before previous was called geometric. In geometric anisotropy, you reach the same seal, but in different ranges. In zonal, you don't reach the same seal. So if I go like this vertically, I see a lot of variation. This is the variogram along the vertical. If I go along this, I'm staying mostly in the same, let's say, strata, and this is the variogram of this image on this direction. I will jump this variogram map. So any questions on the variogram? So the idea is that it is average dissimilarity or average correlation, and that we need to model it, and we need to model with specific functions. All right, so let me talk about an intuitive way on kriging in general, first of all. So here is paint. Here is a study area. Excuse my surrealistic drawings, which here are some data points. And here is an Excel spreadsheet. The data coordinates, and Z is the attribute, okay? Let's call the attribute. All right. So if I first show you a set of data, the data here. So I extract this data from this Excel, and I telling you that here are the data. They have a histogram. Let's pretend it's symmetric for now, and let's pretend it has a mean called mu of z, and it has a variance called sigma z. All right, and I don't show you where the data are, so you don't have access to x and y, and I throw you here in the region here. I'm telling you now, please tell me what will be your best guess about, let's say, precipitation or whatever conductivity you're dealing with in this particular location. What would be your answer? First of all, you would ask yourselves: Is there where I would look at the information from? Where is the information that I can use to answer this? It's in the data, all right, and it's in the histogram of the data. So, any takers? Well, if I have no, if nobody is gonna kill me if I give a very bad, very extreme answer or a very low answer, I could simply say the mean. All right. So if the mean here, so I would say the mean here is my best guess of the precipitation value here. All right. And if I throw you here, and again, you don't know where the data are, all right, what would be your best guess? Do you have any information to change the mu z? The same as before. All right, good. So if I throw you anywhere, your best guess about this precipitation in value would be the mean of the data, because you don't know where they came from, unless of course you have some information that says, well, this part of the domain is different than this part of the domain. All right, and then in order to have these, you would then need to have two histograms. All right, one from the data that came from this, one from the data from that, and then you would say the mean of the one in the here and the mean of that in here. But if I don't have this information anywhere here, my best guess would be the mean. And if I ask you what is the uncertainty in this estimate that you gave me, what would be your answer? The answer would be the variance of this, or the standard deviation of this data. Okay, so if I throw you here, your best guess would be to imagine a distribution of possible answers for precipitation, which is the same shape as the data histogram. If I throw you here, you will be imagining the same thing as the data histogram. If I throw you here, you will be doing the same thing as the data histogram. This is called stationarity, which means that your initial idea about what is the variability and the processes here essentially is everywhere the same. There is no reason for you to believe that you have different values, different numbers, higher numbers here or there. And there is no reason for you to believe that the uncertainty in saying so would be different here or there. So that means that initially you imagine there's Gaussian huts everywhere, and these Gaussian huts are actually the same as the histogram here. Okay, so kriging will actually now once you see the data actually, first of all, you see the data in terms of pairs and distances, and that allows you to create the Varga model. So the Varga model can come without actually knowing the precise definition of where the data, the location of where the data are, but you can just know how far they are from each other. All right, that's we can create a Varga. But at the end of the day, what we will do now is, once we know where the x and y are, All right, we will go in and we'll change these distributions so that when they are close to high value data, they will have high mean and low variance. Why? Because if you're close to data, you have a low uncertainty. And away from the data, far away from the data, then what would be your guess far away from the data? What would be your best estimate far away from the data? There are two options. Either the so if you're here and if I'm throwing it here, you can take the value of the closest value that you're far away from, or you can take the average essentially of the data and say, well, I'm far away from the data, so my best guess is the mean. How would you quantify how far you are away from the data? What is far? Is the range, is the variogram range. Okay, so when you are at distances beyond the variogram range from data locations, your best guess would be the mean. Your best guess about the uncertainty will be the variance of the data, or the CIL of the variogram model, actually. Sorry. Okay, so kriging essentially changes these distributions into distributions that have different means, different variances, and the estimate is the kriging estimate is the mean of the distribution. These are called posterior distributions after you see data, locations, and values. So if you only see the data values, you can only make these statements. If you see both data locations and data values, you can make statements like the ones I told you before. Okay, let's, so I'm gonna just show you, because we don't have really that much time, what are most of the things here in the kriging part. So the idea behind kriging, you get the predictions and the variances. The variances are small at the data locations. We don't need to talk about the notation. These are just the kriging equations, sorry, notations. So there is a difference between what is called simple kriging and other forms of kriging. Simple kriging assumes that you know the expectation of the data, which means that mean value that I was talking about, it is known to you. Now, typically, this is not known to us, but we estimate it from the data, and the difference between whether we know it or we don't know it is, if we know it, we estimate it and we forget about the uncertainty. If we don't know it, we estimate it and we include the uncertainty part. So if we do simple kriging, we assume that the mean is known to us, either coming from the data and not caring about the uncertainty, or somebody whispering to our ears, which is very unlikely. All right, so simple kriging essentially assumes a known mean, and most of the times that mean is constant because we don't have other ways of making this different. If we have auxiliary data, then we can combine the data that we have with the auxiliary data to create regressions, and these regressions essentially will change the mean from different places. So if I was to go back to my paint example, so if this was my study area and I had information on elevation, essentially, I could first build elevation and precipitation, let's say a model, either parametric, non-parametric, with classical statistics, with machine learning, whatever, and that would actually be my mean. So if I was to throw you here, and before you would tell me MZ is your answer of the mean of the data, now you know elevation. So since you know elevation, you go here, let's say this is the value, you go here, you click here, and that would be your best guess. Okay, so if I throw you here, you know elevation here, let's say this is the value of elevation, you go here, that would be your estimated mean. Okay, so when we use different variables together to do kriging, that's called kriging with an external drift or kriging with a trend model. When it happens that those variables are not physical variables but are coordinates, then the regression involves the x or the y or the x squared or the y squared or the sine of x, essentially functions of coordinates, and the dependent variable is precipitation. Then we're talking about universal kriging. So universal kriging links the mean to functions of the coordinates. All right, so external drift kriging links the mean to functions of physical variables such as elevation, temperature, whatever else. Okay, and when we have essentially no information, but what we choose to do is estimate the mean locally within some neighborhoods. Sorry. And assume it's constant within the neighborhood, that is called ordinary kriging. So simple kriging, SK, the mean is known. Ordinary kriging, the mean is not known, but is estimated within different neighborhoods. All right. Universal kriging, UK, the mean is a function of coordinates. And external drift kriging, kriging with external drift, KED, kriging with an external drift, the mean is a function of physical variables. Okay? So what we do is basically we make regressions, we compute the residuals, and then we interpolate the residuals in space. That's basically, in a nutshell, what we do behind this. Okay, so again, these are only equations. So what we need in kriging, we need two sets of distances. We need how far the data from the target is the M, and the data are 1 to n, and how far the data among themselves. So this is the distance between the source data points, the data values, the data samples. That matrix, so here is the matrix of the distances between this point, and these are some data, arbitrary data, and this is the distance matrix between the data. We use these distances through the covariance model, the Van model, to create essentially, to take these distances and pass them through the model. This is an exponential model of a correlation, and make them correlations. All right, so here these are similarities. So what we're saying here, that the number 1 is 0.34 similar to the location here. Number 2 is 0.26 similar to this location, and so forth. Now, if this was alone in the universe and there was no other point around it, the weight I would be giving to this number to estimate this is 0.34, it turns out. But because there are neighbors around me, this number has to be distributed among the neighbors, right? Each one has its own, essentially, link, weight, and these essentially are also distributed among them because the data are correlated among themselves. Okay, let's make an example. Okay. I have a data point here, and I want to, and another point, let's say here, and I want to estimate this part here, and I have another point here, another configuration, and I want to estimate this value here, and the distance here is 10, and the distance here is 10, here is 10, and here is 10. So here is 10, this is 10, this is 10, and this is 10. Okay, The inverse distance method would give the same weight to this, the same weight to this, the same weight to this. Why? Because inverse distance says how far a data point is from the place that you're trying to estimate. But these configurations are different. Actually, here, your prediction is actually better, is less uncertain from the prediction here, because this prediction involves data that are too close to each other. Too close to each other is almost if I know one, I know also the other. Why? Because they're correlated. All right. So one of the major differences between kriging and other data methods is that kriging actually looks not only into the distance between the data and the point you're estimating, but also how far the data among them. So it actually downplays the clusters in the data. So it distributes weights that it would give to the data when they're in clusters. Right. So also, if you were to predict, let's say, if I have this configuration, I have this point here, and I want to predict, let's say, 10 kilometers away, and if these 10 kilometers are in Sahara, or if they are in the Alps, it's a different story. Okay, so the configuration of the data might be the same, but the attribute might behave differently, might have a different roughness, a different smoothness. That is also accounted for in kriging. Okay, so I'm gonna go forget about this. Essentially, the idea is that all these are you can leave these different types of. So the larger the range of a model, the more weights are given to data. In the case of a Gaussian model, you give a lot of weights to the close data points. These are the weights given from kriging. And what you need to remember is what is the behavior of the kriging mean and the kriging variance away from the data and close to the data. So when you are far away beyond the correlation lengths, all the weights are zero. So your best guess is the mean, and the uncertainty is actually equal to the CIL of the model, which is the variance. When you're predicting, so 26 is the number of the slide. When you predict the source data point at the sample data location, you identify the known value, and your uncertainty is zero. And anywhere in between, it's a function of how far you are away from the data, what is your Varga model, and how far are the data among themselves. Okay. A lot of cases we're going to use kriging with local neighborhoods. Ordinary kriging with local neighborhoods is the most widely used method. When you look at the distribution of kriging estimates, you might have you typically smooth, which means that you overestimate the low values and you underestimate the high values. That's called regression towards the median or the mean. If you were to compute the variogram of the kriging estimates, this is the variogram of kriging estimates, and this is the variogram model that you used, they're going to be different. Why? Because there is smoothing in kriging. All right, and kriging was not meant to give you the best map, it means to give you the best single value at a point. We said about this. How do we assess interpolation? We typically do it through cross-validation. Cross-validation essentially, validation data are data that are not used into the kriging or to the regression or to whatever model you're building. These data, how many would we use and where should those be? In order to avoid answering these questions, we use leave one out cross-validation, where we hide one at a point at a time, we estimate it from the remaining ones, we put it back, we compare the estimated value with the true value, we get a cross-validation error. We go to the second data point, we remove it, we estimate from the data around it, we put it back, we compare the estimation and the observation, we get a second cross-validation error. So we get cross-validation distributions. We would like those to be centered at 0. So I prefer this versus this. We would like cross-validation distributions to be symmetric. So if you have a method that produces this cross-validation error distribution, you prefer it over another method like that produces this. And you would like to have centered distributions at 0 and the smaller spread. Okay. Typically, you measure stuff through the mean squared error or the root mean squared error. So you would look at the average error, the cross-validation error. You would like to be close to 0 or as small as possible. And then you would also want a small RMSE. This part here is essentially a summary of the kriging part. We need to know the mean in simple kriging, or we also need to know the variogram, and the weights are marked essentially a part of the variogram. And you can use also sampling designs with kriging variances. Ordinary kriging is with moving neighborhoods, assuming this is unknown, and we estimate it from the data in the neighborhoods. We can use data of different supports. We don't need to worry about this. Measurement errors. If the data have measurement errors, then we can filter that measurement error, and there is no reason to reproduce the data. This is called factorial kriging, and I'm also almost done. And here is where I was saying before. So ordinary kriging is an unknown but constant within the neighborhood mean. Universal kriging is when the auxiliary data are functions of coordinates. And kriging with external drift is essentially kriging done with other variables apart from coordinates. So here is a regression model on precipitation and elevation. Here is essentially using more elaborate regression models, all right? And then you can see that you can make a regression with auxiliary variables and then kriging using that regression model. That was it. There are also other types of kriging, indicator kriging, log normal kriging, and disjunctive kriging to deal with non-Gaussian data. The list is very long, and we can take a lot of classes for this. So it's just a general overview of the kriging equations and what is behind it. And you will hopefully have a better grasp on this once you get to the tutorial of the exercises. The questions that I have for you for the exam is essentially basically most of what I was talking about today. So what is the difference between the different types of kriging? How is kriging different on different other methods? Things like that.